Welcome to the lecture series on neuronal dynamics. In this lecture, we apply the Fokker-Planck equation in order to analyze the network states of the Brunel network. So, in this application of the Fokker-Planck equation, we look at a coupled network of leaky integrated fire neurons. Neurons come in two different types, excitatory or inhibitory. Now, all neurons have the same parameters, which means they have the same time constant, they have the same reset potential, they have the same threshold, they have in principle the same connectivity. The only difference is that one of the populations sends out excitatory spikes and the other population sends out inhibitory spikes. Now, this is a combination of assumptions where it's still possible to calculate network states analytically. So we have two types of neurons, excitatory and inhibitory, but in all other aspects they are completely the same. So I can nearly treat them as a single population. Let me remind you of a couple of simulations that we have seen in a different video. It's a network of 5,000 neurons. Each neuron in the network receives 500 inputs from other neurons. And these input connections are random. And then we can look at the population activity for a network of size n equal 5,000. But we can also look at the input for one or two or three of these neurons. And this gives the membrane potential trajectories or current trajectories just below. And now we can do the same for the network with n equal 1,000 neurons. Now the population activity now averages over 10,000 neurons instead of 5,000. But if you look at the input, then the variance of the input is exactly the same. And this is what we are going to exploit now in the context of these Fokker-Planck equations. So what are the exact parameters? I said 5,000 neurons, but there are 4,000 excitatory and 1,000 inhibitory neurons. And the input is on the left side and on the right side 400 excitatory and 100 inhibitory inputs per cell. Now let's analyze this. What we observe is the fluctuations of A decrease, but the fluctuations of the input and of U, of the membrane potentials, they remain the same. And the reason is that our diffusion process has an amplitude sigma squared, which is controlled by the number of inputs. Now we have 500 inputs, 400 of them will have a positive weight, 100 of them will have a negative weight. All neurons are the same, all receive the same input on average, different realizations, but the same input. So all the input rates are in fact the same. All the input rates are equivalent to the population activity rates, which we can measure. And therefore, the diffusion part is the same for both networks. So why is the population activity of smaller variance in the case on the right? Well, the reason is simple. We average over 10,000 nearly independent samples instead of 5,000, and therefore the measurement noise is smaller. Again, what was simulated? We simulated leaky integrated fire neurons, which receives excitatory input pulses and inhibitory input pulses, which give a mean contribution and a noise contribution, and already discussed the amount of noise. Now we are in a coupled network. So each neuron in the network, I've pulled one neuron out, receives the spike inputs of 500 other neurons in the network. This spike arrival looks noisy. It's a leaky integrated fire neuron, but in the presence of noise, its frequency current curve might be the green one. Now in a coupled network, the coupling, the effective coupling, leads to a feedback that we can analyze by this diagonal line. And now you see there are different solutions, and we are interested, for example, in the solution here, the high activity state. So these are solutions under the assumption that the network activity, A of t, is constant in time. Then we can construct this self-consistent solution where we say the input itself is generated by the population activity, and then it depends on the coupling strength as is given here by the charges. Again, the specific connectivity scheme is now the following. We have a certain number of excitatory neurons, and we have only a quarter of inhibitory neurons. So if on the left it's 4,000 neurons, then inhibitory neurons would be 1,000. Each neuron receives exactly kx excitatory inputs and 1/4 of inhibitory inputs. Well, take a neuron here. If there's only 1/4 as many neurons here and you make stochastic connections, then this neuron has also the chance to receive only 1/4 of the inputs compared to what it receives from the excitatory side. Now, since we have the two contributions, excitatory and inhibitory, we can play the trick and say, roughly, apart from the sign, they average out. Now, I need 4 times as many inhibitory neurons to get my number of excitatory neurons. So I make my absolute strength of inhibition G times stronger. And now you see that G equal 4 means that on average, excitatory and inhibitory inputs are just balanced. And now we will analyze the network as a function of this parameter G. So you see the parameter G here along the horizontal line. And on the vertical line, you see the total input, a total drive. Now, if the total drive is below this horizontal dashed line, then we are in the quiescent state, no activity at all. If the input is above this line and the G factor is small, then we are in a SR regime, synchronous regular. And in synchronous regular, you see that different neurons, they line up visually in these stripes. And that means that neurons fire in synchrony. Not all of them, they might be shifted to each other, but you see here this regular firing pattern A of t. If we make G larger than 4, then we are on this side, then we have an interesting regime which is called asynchronous irregular. Different neurons fire at different moments in time so that on average the population activity is nearly constant. So you see here the scale is 0.1, here the scale was 2, so it's really a different network state. And this is an interesting network state because different neurons fire at different moments in time. There's always some neurons that sit just below threshold and others just had a reset and are farther away. Now for other parameters, you can also get synchronous irregular regimes where you have population bursts but at irregular moments in time, or you can also get a fast synchronous irregular regime. So network analysis allows us to predict analytically different regimes, and then if we run simulations, then we see different firing patterns. These are results of Nicolas Brunel. The paper of Brunel from 2000 has been very, very influential in understanding cortical activity. To summarize, The Fokker-Planck equation is useful. It describes distribution of membrane potential. You can do this as a function of time, not just a stationary regime. We can say, okay, there's a typical drift, there's a typical diffusion effect, and then we have a source term due to the reset. And you can also think of the boundary, the threshold, as a sync term. I presented it as an absorbing boundary condition, but instead one could also say, okay, there's a sync term that removes a certain amount of membrane potentials at the threshold and re-injects these as a source at the reset potential. So here we considered two interconnected populations, and we assume that all neurons are of the same type. Then each neuron receives K excitatory inputs and K inhibitory inputs, and therefore all neurons receive statistically the same input. The actual inputs are different because each neuron has a different realization. It sees input from a different subset of neurons. And then, of course, the sign of excitatory and inhibitory input spikes is different. In the model, it was assumed that the excitatory group is 4 times bigger than the inhibitory one. And then important parameters, then this ratio of how much charge is given by excitatory or by inhibitory inputs. And if this ratio is larger than 4, then overall inhibition dominates. The excitatory group is 4 times bigger, but inhibition is overall still the dominating factor. And this is the regime where we saw asynchronous irregular firing.